Okay, so today we will talk about the boxes and devices. Yeah, boxes and devices. Now, I'm not teaching you the code. Somebody else is teaching you the code. What I'm doing is I'm just walking you into some terminology. Chances are that before you leave the school or shortly after, there will be some subtle changes because the code always gets updated, the CEC, Indian Electrical Code. But what I'm doing here is I'm giving you the beginning, the start on terminology and on some of the techniques and anything that you would need to carry you further once you get the further courses. All right. Okay. All right. Are we going to be able to see our quiz result? I want to know which questions. Okay. So Alyssa, send me an email and I will set up a session with you if you want to go over your test. No problem. I'm glad you're asking that question, actually. All right. Okay, boxes and devices. All right, the Canadian Oh, first of all, there is a funny picture. Yeah, no problem. Funny picture. And as I go along, after I took this course over sometime around 2018 or 17, something like that, I keep updating the pictures because I like to have my own pictures of things. However, this is one of the original pictures that I left from the original presentations that I was handed over. Because quite frankly, it's hard to find something like that. Well, the idea is to show that even though we have electrical boxes and sometimes you can fit more wires than others, it's not a free game. It's not just how many wires you can pack in there and get away with it. All right, so there are certain rules that we should follow as far as the fill ratio is concerned. What's a fill ratio? Well, it is the amount of content that you can put in the box against the volume of the box. All right. Now this goes to the boxes or the device boxes, and this also goes to the electrical tubing. And I didn't say EMT because EMT stands for electrical metallic tubing, but we also have a PVC tubing as well. So you can also fill only so much into that before it gets illegal. All right. So today we'll talk about that, and we will go over some of the terminology and the boxes and the devices that you might encounter as you go along your journey here. Okay, so I'm going to read this statement here. The CEC determines the amount of wires an electrical box can hold based upon the following. Okay, the total volume of the box, and usually that is in North America here, well, pretty much everywhere right now. It is expressed in milliliters. All right, that ml stands for milliliters, so it's thousandths of a liter. Okay. Now, also what's being considered is the size of the wires in American wiring gauge. Okay. So and the type and the size of the device that is inside the box. It could be a switch or it could be a GFCI, and the number of wire connectors that are used inside the box. So basically, we have a box that is a certain size, and we have to consider everything that goes in it in order to be compliant with the code, in order to be legal, right? Okay, so so that's the thing right here. Now, keep going here. All right, so here's the table 23, number of conductors in the boxes. All right, now there are different types of device boxes, Box dimensions. So here is the box dimension, trade size. All right. We have the octagonal box, square box, round, and we also have a device sizes. All right. Now, so here we have the sizes in inches. All right. Now the capacity of the box in milliliters, and in brackets we have cubed inches, not square inches, cubed inches. And maximum number of conductors per gauge. Okay, so let's just analyze it a little bit. We're not going to go through the whole thing, because once we do 2 or 3, then you're going to follow the same idea down the table here. So let's say we have octagonal boxes, a box. All right, so octagon. All right, so 4 by 1.5 inch. All right, what does that mean? Well, we have a box, electrical box. So square box would be something like this. Okay, I'm trying to do the square instead of the Pulp Fiction idea of a square. Now, if you go like this, and if you go like this, and you go like this, and you go like that, and here, and here, and here, and here, now you have an octagon. All right, 1, 2, 3, 4, 5, 6, 7, 8 sides. Okay. Now that's an octagon box. So what do we have here? We have 4 inches by 1.5 inches. Okay, so I'm just gonna erase those helping lines here. Yeah. Quickly. Here. Here. Okay, so sort of we have the octagon, and we have 4 by 1.5 inches. Box used for light bulbs. Yeah, that the octagon box will hold something that's called the lamp holder, which we will talk about as we go along this presentation. So 4 inches. So 4 inches would be the, if you will, the diameter of the 4 inches, and here, something like that. That would be the depth of the box. All right. So 1.5 inches would be here. All right, so the last number usually is going to show you the depth of the box. So if you read the number back, I mean not backwards, but from the last towards the front, the last number is going to give you the depth. All right, so we have an octagon box, octagonal box, 4 inches by 1.5 inches. All right, so now it is calculated that the volume of that box is 245 milliliters, right? Or 15 cubed inches. Yeah. So that's the volume of it. And here we have different sizes of wires. So here's the gauge 14, gauge 12, 10, 8, and 6. And we know that gauge 14 is the thinnest. Then as we go along and we reduce the number that represents the gauge, then the wire gets thicker. Okay, so this is the thinnest, this is the thickest wire. So we can, in that one, we could fit 10 conductors that are 14 gauge. But as the wires go thicker, we are able to fit in less wires in order to be legal. Okay, so the 12 gauge wires or conductors, we can fit only 8. Now wires go thicker, 6, now gauge 8, 5, and gauge 6, which is quite thick. You're not going to see much of that. However, this thing is listed only 3 wires like that, or conductors. Right? Then of course now we can see here, now there's a deeper box, right? Still it's an octagon box, so that the diameter is still the same. It's 4 inches by, now it's an inch deeper, almost an inch deeper, 2 1/8 of an inch, right? So of course it will have more volume per shape, and so it's 344 milliliters, or 21 inches cubed, and then we can fit more wires because the box is bigger. All right, so 14 gauge wires, we can fit 14 conductors, 12, all right. Number 10, 9 wires, 8, 7, and gauge 6, only 4 wires, all right. Then we have a square box. Again, only one size here as far as the sort of, not a diameter, but we only see one side because it's a square box. So of course it's 4 by 4, right? So you can just, it's okay just to list the number 4 here. And then 1.5 inch deep and 2.5 inches. And then there is there are some different sizes as well here, okay? And then based on that, the volume is listed and then how many conductors you can fit in that round. So over here, okay, actually here, the last one will be a 1/2 inch. Actually, this one should be 1.5, okay? And then you can, actually this is 1/2 inch because you can fit only 3 wires here, 2 wires. So that's a very shallow box. Excuse me. Based on that, you can follow this table in order to find out how many conductors you can fit in that box. By now, you probably have noticed that reading the Canadian electrical code, or pretty much any electrical code, whichever country you're in, you are going to pretty quickly find out that it's almost like reading materials to study to be a lawyer, right? So it's almost like a legal language, and it is legal language. Quite often you're going to see that a lot. So it takes a little bit to get used to some of the terminology and some of the phrases as they are formulated, all right? So now what we need to find out, and I think a couple more slides here, that one there, yeah. Because over here it says maximum number of conductors, but because everything has to be buttoned up, everything has to be described, you are going to find out what it is that is considered as a conductor. So there is no any silly arguments with a lot of unknowns, okay? So here, table 22, space for conductors in boxes. See the rule 12-3024. Just get my mouse out of there because it's just blocking my view. All right, so size of the conductor, all right, and usable space for each insulated conductor in milliliters, okay? So gauge 14 takes about 24 milliliters as it is in the box. Now the length is not specified here. Now 12, 28 milliliters, and so on. So you can notice that as the numbers go down, the thickness goes up as far as gauge is concerned. So of course the volume of that object, because the conductor will be an object, goes up. So it makes sense. All right, now here I'm going to zoom in a little bit. Yeah. Not going to go over the whole thing, but I just want you to get a couple of points here. And you will study this thing a little bit further and deeper as you go along. Maximum number of conductors in a box. Okay, so here's the lawyer language, so to speak. All right, boxes shall be of sufficient size to provide usable space for all insulated conductors contained in the box. And here's subject to the following, which means basically considering. Okay. A conductor running through a box with no connections, and here's the lawyer language, therein, all right, shall be counted or considered as one conductor. Again, let's repeat that. A conductor running through a box with no connections. Right? So it's basically, here will be a box, right? Whatever that box is, and this would be a metallic tubing, for example. All right, maybe from all the three sides, let's say, okay? So if there's a wire going inside that, and it enters the box and it leaves the box, but it is not connected to anything, right? Maybe there's another wire here that enters and goes that way, all right? So over here, according to that table, we have two conductors of whatever gauge, okay? Because here's a wire, or conductor, I keep calling it wire. Here's a conductor entering the box and leaving the box, so it goes through the box, and it's not connected anywhere to anything. Okay? So one of those should be counted as one conductor. So we have two of those running. So this box right now, as it is, contains two conductors. Okay? Now let's see here. Each conductor entering or leaving a box and connected to a terminal or connector within the box shall be considered as one conductor. Well, let's just analyze this picture here again. Let's say we're going to terminate this wire. We're going to cut this through. Right? We're going to separate that wire. And this wire is going to be connected to some sort of a device. So now, out of that one conductor, we have two conductors, because there's a wire coming in, it's connected to something, and there's a wire also coming in, it's connected to something. So now we have three conductors inside the box. Okay. So let's look at this thing again. Each conductor entering or leaving the box, and the conductor that is connected to a terminal or a connector within the box shall be considered as one conductor. Okay, so we got that one out of the way. All right. Now, a conductor of which no part leaves the box shall not be counted. All right, let's analyze this here. Let's say there is another connect. Let's say these two something was done that this conductor was cut. All right, interrupted here. And let's say somebody at some point decided, no, let's reconnect that. Or there would be some existing installation and something was connected, but now nothing is going to be connected. We're just going to use that wire, whatever. And you decide to make it a pigtail. So we're going to put a wire nut connector here and put one here. Okay, so now this wire is connected. This conductor is connected. So now, how many wires do we have? We still have two conductors, because here is a conductor that is connected to a terminal or connector. So here's one, and here's another that is connected to a terminal or conductor, and there's a conductor. Here's a connector. Sorry, conductor. Yes, a wire connector. Conductor. Conductor. That no part of that leaves the box, so this one is not counted, right? So how many conductors we have here? Which is whistling, which is not? Now, seashells, seashore. There we go. So here's a one conductor that goes through. Here's another, and it's connected to a connector. Here's another that's connected to a connector. So altogether, we consider here as this box contains three conductors, 1, 2, and 3, and the one that no part leaves the box is not counted. It's just the way it is, right? All right, and then number is wire supplying. Now, okay, so here number 18. Okay, wrong mouse. Number 18 and number 16 gauge fixture wires supplying a luminaire mounted on the box containing the fixture wires shall not be counted. All right, so what's a luminaire? It's a light fixture, like for example a light fixture for a ceiling fan or any like a chandelier type of a thing. All right, so if you have a box mounted in the ceiling, those wires that are coming out of the light they shall not be counted for some reason, right? And that's as far as I'm going to stop here. Then if we continue with that one there's going to be too many references. And you know what? With this one here, you can take up on when you study the code. I'm just giving you the entry point to the code on this one here. I'm pretty sure you are already studying the electrical code to some degree of intenseness, if you can say that. All right. What do the boxes look like? So here's okay. So here's going to be some terminology here. Let's take a look at this device box. A single gang device box. So okay, so there's a device box. It's a box, and it's a device box. So it's a box that is designed to accommodate whatever device. It could be a switch, it could be a receptacle, or whatnot. All right, now let's see the dimensions of that. Now we have two dimensions in front of the depth. So the last one is the depth. So now we know that this box is 2.5 inches deep, right? And it's 3 by 2. So 3 is the longer side here, and 2 is the shorter side. And here is a single gang. What does that mean? That means that this shorter side is 2 inches. Right? That's a single gang box. Right? This box can hold 8 14-gauge conductors, described as in that lawyer-like document that we just saw in previous slide. Right? So again, the device box, we know that's 2.5 inches deep, and it's 3 by 2, so 3 inches by 2 inches here. That makes it a single box. This 2 inches part here, that makes it a single gang. Okay, now can it hold 8 even when a device is in? That's a good question. Let's keep going with that. All right. That depends on whether you are doing, that depends on the size of the device, okay? If you just have a regular device, yeah, let's just keep going with those. It's going to become clear. Okay? Now, single gang. Now, single gang device box, all right? Most common size and uses. All right. 3 and a 2. See, single gang, you always have that second shorter side 2 inches. It's a single gang, right? And this one here, this dimension here, that's the depth of that box, and this is 3 inches. That's mostly going to stay the same. This number is going to change as we double gang them and triple gang them. All right. So number one, 3 inches by 3 by 2. So it's a single gang box, 2.5 inches deep, for duplex receptacles and switches. So duplex receptacle is the device that we already have played with during our first lab. And now it's recommended that if you want to use GFCI receptacle, you are supposed to use 3 inches by 2 inches and 3-inch deep. So you are going to get the deep box for that. Why do we need the deep box for this? It is because the GFCI receptacle is larger in volume. Just a regular, if you take a look from the side, if you look at the duplex receptacle, here is the front, that's where the prong, that's where you plug things in, okay? And here is the body of that receptacle, and you have a screw, and you have a tab that's connecting those two screws, okay? So it has certain depth here. Okay? That will be the duplex receptacle. Now, if you have the same receptacle, but it's a GFCI, and we'll talk about what that is, that thing is quite deeper because it has to contain some some circuitry inside. Okay, so you're the prongs, and so it's deeper device. So you will need a deeper box to accommodate the same amount of wires that if you want to use. GFCI. What is a GFCI? I'm pretty sure some of you already know that, but most of us might not know that. GFCI. GFCI. What does that stand for? Okay. Well, I will give you the abbreviation, the acronym meaning for that is ground fault circuit interrupt. Does it tell you anything more? Maybe not. Well, let's talk about maybe you already had that. If not, you will study that in more depth, especially in your DC circuits class. The Kirchhoff's law, the first Kirchhoff's law stands for whatever comes in has to come out. So let's say, you know what, I'll just lower the light a little bit so you will see less of me. And you will study this further. I'm just giving a flash of that, okay? Now, let's say we have a power supply, a resistor, and we have a closed circuit here. Okay, of course, the longer side of the power supply is the positive side. Here's the negative side, and if you consider the here's the resistor R. If you consider the conventional current flow, you're going to assume the current flow from the positive to the negative side, as opposed to the electron flow, which would be different, and you will study that as well. So let's just say conventional current flow. The current flows from positive to negative. So this amount of current, there's nowhere else the current can go. Okay. So this current at this point is same as the current at this point, same as the current through this resistor, same as the current here. Anywhere in that single branch circuit, the current is going to be the same because it has nowhere else to go. Let's say you're going to have whatever device here, right? And this device is going to have some connections inside. And also the chassis or the housing of this device is going to be grounded, right, or bonded. If something happens inside that box, that some of the current is going to escape to ground, then this current here is going to be larger than that current because part of the current is going to escape to ground. So this current will be more than that current because some of it is going to escape here. It's just like a water leak, right? Same as if, for example, one of the wires becomes detached by accident and it touches the chassis, the ground is going to take the hit. So when you touch that metal box, the electricity is not going to flow through you to the ground. It's going to have a straight path to the ground. That's why we bond the things, or we ground the chassis. All right, so now there is let's say there is some sort of a device here sensing that current leaving and current coming back to the power supply. If those things are not equal, that device is going to interrupt the circuit. It's going to shut it off because something is happening that is not supposed to be happening. The current is supposed to be leaving, going through whatever load is, coming back here and coming back into the power supply, and whatever comes out should come in. There should be no escapees. There should be no anywhere alternative paths for the current. If there is, then there is something wrong. Excuse me. And that is going to react and shut down. So if something happened here and some of the current escaped to the ground, so we would have something that's called a ground fault. Okay? So ground fault. Upon the ground fault, the circuit will be interrupted. GFCI, ground fault interrupt. So that is that circuitry, the sensing circuitry is somewhere inside that GFCI receptacle. And it also has the input terminals and it has output terminals. So you're connecting that supply wire or supply cable into the input terminals of the GFCI receptacle. And from there, you can connect consecutively other receptacles And whatever happens here, this circuit is going to sense that. If a ground fault happens here or here, it is going to be sensed by this first one in line, and the circuit is going to be interrupted. Most of the time, you're going to see these type of GFCI receptacles and on kitchen counters, around the kitchen counters, or anywhere there's a water in close proximity. Because when the water gets inside a device box, water does have some conductivity. Water conducts. So some of the electricity through the conductivity of the water can escape to the ground. And if that happens, then the current leaving and current coming back is not going to be equal. They are not going to be equal to each other because some of the current is going to escape to the ground. We will have ground fault and the circuit will be interrupted, GFCI. Right? So that's the thing. So that's why those things are bigger, the GFCI receptacles. GFCI receptacle needs to be installed if near the sink, for example, yes. Okay. Bathrooms or even those outside. Now, you can have, because just the first one in the branch has to be GFCI, so you can install the first in line as GFCI receptacle, or you could have a circuit breaker in the electrical panel, that the circuit breaker is going to be the GFCI circuit breaker. Then on that branch, you can just install regular duplex receptacle or receptacles, and they will be GFCI protected by the circuit breaker that's inside the panel. You will also study that further, and you will have some practical, you'll be exposed to some practical knowledge when it comes to that, right? So let's go back to the thing here. So this our projection, if you can call it that way. So now let's read it again and see if we have more understanding of that. Single gang device boxes, most common sizes and uses: 3 by 2, 2.5 inches deep for duplex receptacles and switches. That's it. Okay, most of the time. Or 3 by 2 by 3 inches, so it's a deeper box for GFCI receptacles. Right? Also, there's another statement here. So now we understand that better, right? Front face of the box extends 1/2 inch in front of the stud for drywall. Right? What does that mean here? Well, when you're installing the electrical devices on a if the drywall is gone, so just bare studs, bare framing is exposed. So here's the ceiling, here's the floor, and between that you will have metal or, let's say, wooden studs. Okay? Not a very straight ceiling, but that's okay. And sometimes you're going to have the horizontal notchings between those. Sometimes we will not. Usually the wooden studs will have the horizontal notchings, and the metal they're open from the top to bottom. Good thing to know, because when you have to run a wire, never mind. So when you install a device box, like a single gang device box for the like, let's say, receptacle, then when the drywall comes on top to cover the wall, that thing would be recessed, would be deep, because drywall is 1/2 inch thick. So if you look at it from the side, right, you just flip that to the side. Here's the stud. You're going to install the box that extends 1/2 inch to the front. And here's the box. Here's your 1/2 inch. So when the drywall comes on top of the stud, the front of the box is flush with the drywall. So that's basically what that means. And a lot of the boxes will have some markings, so you don't have to use your tape measure, and you can do things quicker. So here, let's read this again. Right? Front face of the box extends 1/2 inch in front of the stud for drywall. Right? So that's basically what that means. Right? Single gang device boxes, devices with devices terminated. All right. So what do we have here? Let me zoom in a little bit. All right. So over here we have a, well, this is something that's called a three-way switch, and we will look at those devices as well, maybe in the second part of this presentation. And there are wires terminated inside that box, so this device box will hold a three-way switch. Now you see here is a GFCI. See, that's that part here is thicker. So now one is input, one is output, and the sensing circuitry for the GFCI. So, no, actually, no, that's not it. Sorry, it's not even Friday yet, okay? What am I talking about? This is also a switch, okay? It's a four-way switch. It's a little bit bigger than a regular switch, all right? Of course, it's a switch, it's not a receptacle. All right. We will take a look at the GFCI receptacle the further slides. Okay, so here's examples of, and now if you take a closer look here, here is the stud, right? And there are some markings here, those like little notches here. And between here and here, it's exactly ½ inch. So if you align the box with those notches, you will have the box sticking out exactly ½ inch right there. These are the helping things here. All right. Single gang device box cover plates. You can tell right away that it's a single gang because it just accommodates one gang. So it's just like a 2-inch, but this is still slightly bigger than 2 inches because the box within that is 2 inches. So this is going to be a little bit wider just to accommodate the, for aesthetics. Right? So this is a face plate or face cover or cover plate for duplex receptacle. And this one, of course, will be for a switch. Right? So quite often you're going to call them a faceplate. And of course, you can also see blank faceplates if you want to blank it out. So you should nothing should be left uncovered. All right, now see here it is, 3 inches over here, 3 inches. Now this is 4 inches. Now this will hold 2 devices, right? 2 gang, or quite often you're going to hear the terminology double gang. Right? Device box, or quite often you're going to hear double gang box. And of course, this size remains the same because you are just adding those devices horizontally. So this 3 inches is going to stay. But over here you have 2 inches and 2 inches. So of course you're going to have 4 inches, and this one here is 2.5 inches deep. Okay, so here's the difference between a single gang box and a double gang box. All right, now 4-inch square box, 4 by 1.5 inches. So of course we only have, because it's a square, we only have to give the dimension of one side, because we know if it's a square, the other side is going to be the same, right? So 4-inch by 1.5 inches deep, and this will contain 14 14 gauge conductors. Not often used in residential wiring, although sometimes it is. Exception for cable connections with no devices. It's another way of saying that usually these kind of boxes are being used, usually, right, as something that's called a junction boxes. Right? All right, usually. What does one say? 4-inch square box used as a connection point or a junction point for a circuit. You see, there are a couple wires going from the top, and there's one wire going from the bottom, and there are some wire connectors placed on that. So there's no devices. There are no devices here. It is being used as a junction box or a connection point. Sometimes you will have to do that as well. Right now, if anybody's guessing what kind of that thing here is, of course, this one is going to say 3-gang device box or triple gang. Double gang, triple gang. Oh, look, this is like 3 single gang boxes aligned in the row. Right? So this would be a triple gang, so it's 3 by 6 by 2.5 inches deep, and this would hold 24 14 gauge conductors. All right. Now we have a lot of time here. We're going to go up to 18 gang. No, just kidding. All right, I'm so funny. All right, here's a 4-gang or 4-gang quadruple gang device box. So here that size stays here. How tall the box is, 3 inches. Now 2, 4, 6, 8. So 8 inches and 2.5 inches deep. And this will hold 32 14 gauge conductors. Let's keep going. See how many gangs can we get. All right. Examples for using such boxes here. This is a recessed plastic 4-gang device box. All right. Anybody would have an idea where this would be used? You can just type or you can pipe in and say it. So TV setup, here we go, flat screen TV, so it doesn't stand out from the wall. So what do we have here? In some of the boxes, when you have multiple gang boxes, not all of them are going to be used, not necessarily they're going to be used for electrical connections, for service connections. So the furthest to the left, of course, that would be the service cables going in because it's a duplex receptacle. But over here, what do we have? We have communications going on all the way to the right. So here's a coaxial cable, which we will study next time I see you next term. And here is a telephone wire. So this would be not service cables. This would be the communication cables or communications cables or signal wires. All right. So here's a coaxial cable, here's a telephone cable, and over here, this looks like, these guys look like speaker cables, and these look like line level signal cables. And wherever they go from behind the wall, they're routed to appropriate devices. Right? For flash mount flat screen TVs, there we go. Right? Sometimes you're going to see something like that. Take a trip sometimes to some electrical supplier store that we have locally around here, or if you're in GTA, because sometimes the GTA is new local, you are going to find some distributors, and talk to Mr. Cunningham, talk to me during the labs. I will give you some of the distributors that they don't sell to the public, but if you go through a registered business, you can get a larger volume at a discount price. Plus, the variety is much greater than just a local hardware store. Although in some local hardware stores, you also have pretty good variety as well. Except you don't get a discount if you are running yourself a business. All right, now, also, there's such a thing that's called Gengable boxes. All right, these are boxes that can be disassembled slightly. And if you have a bunch of single gang boxes, you can join them together to make double gang boxes or whatever amount of gangs you want. And this is how you turn 2 single gang boxes of that sort. Not all the boxes are capable of that, but there are those. Oops. How far did we get with that? Okay, here it is. I want you to see some of that. Yeah, not all. See that the wall, this wall was removed from one box, and of course this wall was removed from the other box, and they are joined just like Lego blocks. Not all of them are doable in this way, but some of them are called gangable boxes, and you can make one solid double gang box out of two single ones. Right? You're going to have in your stock or in your working van a bunch of those because when you're in a pinch, when you have to make one or two device boxes like that, it's a good idea to have it handy or have it close by, so you don't have to go to the store and make an order or order online and wait for it. So you can just now, if you have a large installation that involves a lot of the multiple gang boxes, of course you're not going to spend time assembling those. You're going to order a specific amount of the specific gang number boxes. So this is the cost versus time type of thing. But it is possible if you're in a pinch. By all means, you can do that as well. Next slide. Oh. Yeah. All right. What do we have? Gengable boxes. Used mostly for adding devices to an existing installation, which would be called retrofit. Retrofitting is adding to an existing installation or disassembling an existing installation and keeping parts of it and maybe replacing the head end or the receiving end. Okay. So that would be retrofit versus what's the opposite of retrofit? The opposite of retrofit would be brand new installation. So gangable boxes used mostly for adding devices to an existing installation, such as retrofit. F-straps, all right, pins, or the F-straps pin the boxes between the inside and outside surfaces of the drywall. Right? If you have a wall and a new installation, this drywall would not exist, and you would mount the box, the device box. Let me just yeah. Go back. Here. You would mount the boxes to the stud, and then the drywaller company would come over and they would install the drywall. Right? Now, when you have a drywall already existing, or when you're retrofitting or adding devices, you might not have access to a stud, or you might not know where the stud is. But if you don't, you can easily find out using something that's called Stud Finder device. But sometimes you're wherever that outlet would be, as the furniture is arranged, you might there might be some piece of furniture or something might be obstructing, so you might have to move that device somewhere here between those two studs. So what are you going to do? Hang it in the air? You can't, right? And if you just screw it to the drywall, it's going to fall out. So something that's called the F straps are being used for that. I would encourage you to just Google later on. It's seriously, it's a short video. It's like a minute and 20 seconds on how to use the F-clips. And those are also a common thing that is being stored in the working vans. They just buy them by kilograms and they just stock them there in the, because you never know when you might need one. Very nifty device, right? That will help you to install a device box in a drywall, so that it's only going to be held by a drywall between the two studs, and it's still going to be okay. Now, duplex split receptacles. We still have maybe 4 minutes, so we're just going to go with, oh, come on. Yeah, I'm moving my mouse too fast. Duplex receptacle. or a split receptacle. Remember when we had that? So there's a screw here, there's a screw terminal here. These two correspond to this prong here, to this slot for the prong here. And of course on the other side, these are connected. Now, this screw terminal accommodates this prong, and this screw terminal accommodates this prong, and there is a tab that connects those two screws. So out of the box, when you buy the receptacles, you will see those tabs intact. But what you can do is you can remove that tab, and it's removable, but you can just grab it by the needle nose, twist it off, and you have that thing interrupted. So this screw terminal only is going to be accommodating this prong, and that screw only is going to be accommodating this prong. And if you leave that one intact, and if you up the gauge of the wires, make it thicker, so the neutral wire is going to be thicker, you can have a split receptacle. So you're going to have the neutral going to these two neutral prongs, and this prong here, the top one, is going to be connected to one circuit breaker, and the bottom one is going to be connected to another circuit breaker. Why do we need to do that? Sometimes, usually in the kitchen countertops, when you have a toaster, coffee maker, and all kinds of devices plugged in the morning, you can overload one circuit. So this way, that gives you two circuits, so you have more amps. So if it's a 15 amp each, so you have 30 amps in that receptacle. So when you plug in a coffee maker here, and then you turn on the microwave oven, then it's not going to draw too much current, or a tea kettle and a microwave, they are going to overdraw, to try to get too much current, and the circuit breaker is going to flip. So this way you can have two separate devices plugged into two separate circuit breakers. Where are we here? All right. All right, so of course, this is the example of the tap being broken, interrupted. So here we have a neutral wire, one neutral wire going to the other side, which will be accommodating the neutral prongs. And over here we have a hot wire, black, going to the top part, and the hot wire, red, going to the bottom part. What is wrong with this installation here right off the bat? I am going to ask you next time, what do we see wrong right off the bat? It just hits you, it just stares you in the right in the eye. This is a no-no with this installation. Jackets are getting caught in the screw. There we go. All right. So here's the jacket. Is pinched by the screw terminal, so most of the connection is being made with the insulation, and some connection, but some connection will be made with the bare copper wire. What is going to happen then, there's a chance of not a very tight connection being made. Yes, too short inside as well. When that happens, then at this point, this is the weakest point in this case, is that things might heat up a little bit to the point that you can actually start a fire, right? Or arcing, yes. All right, there we go. Now, is this the last slide, or is it second last slide? All right, devices used with gang boxes. Here's a 20 amp GFCI, 20 amp, and you can tell that this is 120 or 110, the regular household voltage. And that thing here suggests, this little slot going sideways, that you can plug in a device that is going to try to draw more than 15 amps, up to 20 amps. If you try to plug that device into a regular GFCI that is up to 15 amps, you won't be able to physically plug it in. Now, if you can plug in a regular device that is going to draw less than 15 amps, because the load decides how much current goes through that, not the circuit breaker. The circuit breaker is not pushing the current, the load is drawing the current. Right? All right, now let's see here. GFCI, here you have a test button and you have a reset button. So if you want to test the device, the GFCI, you press the test button and it should pop. It should pop the reset button here. And then if you want to reset that, you just push it back in. Different footprints for the different receptacles. There are some of the, these 15 amps 125 circuits used in homes built before 1960s. Slots are different sizes to accept the polarized plugs. So here will be neutral, here would be the hot, but we don't have a grounding or bonding terminal. Now we are not installing those kind of things. We're installing bonded receptacles. And this one here would be just the same voltage, 125 volts, but 20 amps, as we saw that. And over here is 220, all right, or 250 volts. And there are different footprints for different, there are many of those, but at least I want you to know these 4. Later on, you're going to know a little bit more. And you know what? This is the last slide, and you still have 1 minute to go for your next class. Have a nice day. Thank you, and I will see you tomorrow. And the test will be active tomorrow after the class. Thank you, and have a good one, guys.